Okay, so we now look more in detail with the aspect of context switching. Right. Before we get into the details, there are some things we need to recollect, right? So we'll work with the assumption that we had process 1 executing, and the what we really want is that we make a context switch from process 1 to process 2, right? So a couple of things that we need to recollect. First is the fact that process 1 has its own virtual address space, right? And within this virtual address space, we have the top part of it, which comprises of the trampoline and the trap frame. Similarly, the process 2 also has its own virtual address space, and the addresses right at the top comprise of the trampoline and the trap frame. Okay. Now, we also briefly studied that we have a kernel's virtual address space, which we call the scheduler's virtual address space, which looks something like this. So, this would be the kernel's virtual address space. Right. So, our objective when such a context switch occurs is to move from P1, that is the process 1's execution or the process 1's virtual address space, to process 2's virtual address space using the scheduling algorithm. Okay. Okay, so this is the first thing we need to recollect. The second thing is the aspect of the context. Now, we have seen this before, and you can actually look back at the video where we started the first process. There is a structure called the context, which I will just pull up from here. Right. So, this particular structure saves the return address, the stack pointer, and the 12 callee saved registers S0 to S11. Right. Now, if we are able to save and restore this particular context, this essentially can be used to move from one context to another. So, using this particular register, we can say move from the process P1's context to the kernel's or the scheduler's context. Later, we will also see that we can move from the scheduler's context to the context of P2, right? Therefore, triggering the context switch, right? Another thing to note is that each process would have such a context, right? And this context is essentially the pointer to this context is essentially saved in the processes proc entry, right? So, process 1 has its context, process 2 has its context, and the scheduler has its context, which is the kernel's context. Okay. So, now let us essentially trace what happens when the timer interrupt occurs. So, we have process 1 that has been executing, right? This is in user mode and it's executing, and now a timer interrupt occurs, right? Now, the timer interrupt, as we have discussed earlier, would be targeted to the machine mode, which then forwards this interrupt in as a supervisor software interrupt to the XV6 OS, right, or to the supervisor mode. So, thus process 1 gets interrupted and and moves from the user mode to the supervisor mode, right. The program counter is loaded with the value of stored in STVec, which holds this particular function uservec. So what's happening here in with our thing is that the timer interrupt eventually stops or moves the execution from the user mode of the process into the trampoline, where we have the uservec function present. So the uservec function looks something like this. It's present in trampoline.s and essentially saves all the user registers in the trap frame. So each register, such as the return address, stack pointer, GP, the temporary registers, S0 to S11 and so on, are all saved in the trap frame. Recollect again that a trap frame is just present one page below the trampoline, right. So one page below the trampoline, all the registers corresponding to the user space essentially is saved, right. Now, one assumption we'll also make is that process P2 has already run before, right, and therefore sometime in the past it was executing, and then the timer interrupt occurred, and its entire context, all the registers and all that, is essentially saved in the trap frame, right. So this trap frame in P2 is essentially filled up, right. At later point, if the scheduler essentially picks up this process P2 and allocates it the CPU, this trap frame or the contents of this trap frame would be loaded into the registers and it would essentially permit process P2 to resume its execution from where it stopped, right. So the trap frame for P1, we are assuming now has the current state of all the registers from the user space, and due to some things that happened in the past, the trap frame for P2 also contains the registers corresponding to the process P2. Okay, so we now have the user vec that executes. It stores all the registers in the trap frame for process 1, right, and at the end it moves from the virtual address space of process 1 to the kernel's virtual address space, which we call as the scheduler's context, or the scheduler's virtual address space. So the function that gets invoked is this function called user trap, which identifies the cause of the interrupt. So recollect, we have looked at the user trap function earlier, right, which essentially looks into the scos registered to identify that the interrupt that occurred was a supervisor software interrupt, right. The user trap would identify this and then invoke the yield function, right. Now the yield function is, as we see over here, present in proc.c. What it does is that it essentially moves the particular process which was in a running state to the runnable state, right. So doing so, what we are actually achieving is that we are now setting we are removing process 1 from the CPU, from executing in the CPU, and inserting it back in the runnable queue, right. So next yield calls shed, which is essentially invoking the scheduler. So yeah, okay, next yield calls shed, which would then invoke the scheduler, right. So shed essentially looks something like this. What is this? Right. So it does certain sanity checks, right. Like for instance, it identifies if the current state is running, and we know that the current state is already set to runnable, but so these are like sanity checks which are actually obtained. if any of these checks essentially fail, then there is a kernel panic. Essentially, it causes the kernel to crash or stop executing. But important for us is this function over here called switch. So, what are we doing here is that switching from the context of process P1 to the context of the scheduler, right. So, recollect, we have again seen this before. The switch function looks something like this, where the context of the current process, that is a context of process 1, which comprises of the return address, stack pointer, and the 12 registers S0 to S11, are essentially stored within this particular context structure, and the scheduler's context is loaded into these registers. So, when this particular function returns, we are now going into the scheduler's context, right. So, this here, this shed which invokes switch moves the CPU from the context of this process, right, into the context of the schedulers, into the scheduler's context. So, when this occurs, we are essentially moving from the schedule to the scheduler context. Now, the scheduler context would is essentially set as follows, right. So, it would, the scheduler context comprising of the return address, program counter, and the 12 registers is essentially, yeah, this is the same thing, yeah, okay. Okay. Now, the scheduler's context is essentially within the scheduler, right. So, what we see over here is the switch statement, and the scheduler, when switch returns, essentially executes the scheduler function, but starts executing from line number 464. Okay. Now, why does this essentially happen? Or this essentially happens because, as we see here, the scheduler itself invokes the switch function to change the change context from the scheduler context to the process context, right. So, the stored scheduler context essentially corresponds to the state of the scheduler at this particular point. So, at this point, we have the return address which is set to 464. The stack pointer corresponds to the state when this function was executing at this particular line, and so on. So, anytime we restore the scheduler context, it essentially goes back and continues to execute from this line, right, line 464. So, when switch moves from the process 1's context to the scheduler's context, we essentially start executing from this point. It goes up here, goes to the next iteration of the for loop, picks the next proc, identifies if it's runnable. If it is runnable, it comes back here, sets the state to running, sets the current CPU to be executing this proc, this particular process, and then switches context to that new process. So, let me repeat this again. So, let me repeat this again. The scheduler's context is essentially placed at this particular point. So, what this means is that the context stored in the register struct context for the scheduler essentially has the return address pointing to this line 464. So, when switch moves from the process 1's context to the scheduler's context, this return address is loaded into the program counter and causes the execution from C proc equal to 0, right. So, after this switch to the scheduler context, the scheduler executes from here, goes here, picks another proc, checks if it's in a runnable state, and then chooses it to be executed. Let us say it has essentially chosen the process P2 to execute, which happens to be in the runnable state, right. So, this P essentially points to the process proc entry or the PCB for P2. It sets the state for P2 to be running and sets C proc to be equal to P. So, C corresponds to the current CPU, which is set over here, my CPU, and we are just saying that the current CPU or the current heart is running process P2. So, now we invoke switch again. So, notice that here we are, the first parameter is the scheduler and the second parameter is process P2's context, right. So, this is what we have, right. Process the scheduler's context is at proc dot c at 460, that is this point. The process 1's context, because the registers have been stored, is at proc.c 494, that is where the switch occurred. Similarly, the process 2's context is also at proc.c 494 because sometime earlier, as we have discussed, process 2 had executed and there was a context switch, right. So, the similar statements had executed and the context corresponds to proc.c at line 494 in the process 2's context, right. Now, what happens when there is a switch over here? So, now as before, the first parameter is in the second case is the scheduler, and therefore, the scheduler's context corresponding to the return address, stack pointer and the 12 registers are stored in the scheduler's context, and the process P2's context are then loaded into the registers, so that when it returns, when this particular function returns, it returns back to the process 2's context, and this happens to be in proc.c 494, right, which essentially is here, but in the context of process 2. Okay. So, now what we have been able to do is, as you have seen, we have invoked switch function twice. So, the first switch function, that is this one, moves from the process 1's context to the scheduler's context. The second invocation of switch moves from the scheduler's context to the process 2's context, right. The process 2 would now continue to execute because the context has been restored. So, process 2 will continue to execute from this line 495. It would essentially execute this int enable, and then that is this particular function, and then go back to the function yield. From yield invoke user trap ret, and then user ret, which is essentially present in the trampoline, which is then going to restore all the registers which are stored in the trap frame for process P2 and return, and finally restore process 2's execution, right. So, there is the important thing to actually remember over here is, while all of these are happening, the process 1's context, which is essentially stored due to this switch statement, corresponds to proc.c 494, right. So, later on in time, when the next interrupt occurs or some subsequent interrupt and the scheduler picks up process 1 to execute, process 1 would essentially continue to execute from the context of proc.c 494 and essentially follow this particular sequence of function calls shed, yield, user trap ret, user ret, and the process 1 continues to would resume execution. Okay, so every time a timer interrupt occurs, this sequence of function calls are invoked. There's multiple context switching that occurs between process 1's context to the scheduler, scheduler's context to the second process, that's process 2. And again, there are multiple modes that are involved as well. For example, when the timer interrupt occurs, it goes to machine mode, then gets forwarded to supervisor mode. Supervisor mode switches the virtual address space, and there's a lot of essentially quite involved things that can occur. So this entire switch from process 1 to process 2 takes some substantial amount of time, which we call as the context switch time. So when we talk about multitasking environment, we have this process 1 executing, then we have this blue region over here, which is essentially the context switch time, where the context switching is occurring, the scheduler is executing, it's identifying a new process to execute, restoring the state of that process, and then causes the process 2 to resume execution. So every time we have a timer interrupt like this, such amount of context switching time is essentially wasted due to the scheduler and other aspects. So what affects this context switching time? So of course, as we've discussed earlier, there is the interrupt latency, where the path taken from the time the timer interrupt occurs to the time the interrupt is essentially serviced. So that is the timer interrupt latency, which affects the context switching time. In addition to this, saving and restoring from the trampoline to the trap frame. So this could also be significant, because RISC-V is a RISC PC, and it's got a large number of registers. The scheduling algorithm, which we will essentially see next, would be would also influence the context switch time quite a bit, and therefore it would be important to essentially optimize the scheduling algorithm, so that the scheduling algorithm can essentially pick, or the scheduler can essentially pick the next algorithm to execute very efficiently, right? In addition to these direct factors, there are also indirect factors that affect the context switching time. So so whenever we perform a context switch, there is essentially a loss of locality, right? The locality is and this loss of locality essentially is manifested in multiple ways. For example, there could be the processor pipeline needs to be flushed. That's a loss in the cache locality. So you will actually see a large number of cache misses, and therefore subsequently data should be brought into the cache from the main memory. So this could also create delays, which indirectly affects the context switching overheads. And also, if you do not have sufficient amount of memory in your system, you will also see large number of page faults that can occur, and you would require pages to be loaded for process 2 into the main memory from the swap space. In addition to this, because now we have shifted from the process 1's virtual address space to that of process 2's virtual address space, a lot of entries in the TLB would be invalid or invalidated, and the TLB would essentially need to be reloaded, right? So recollect that if the mapping from virtual to physical address is not cached in the TLB, then the processor would need to do multiple accesses, perform page table walks through the level 2, level 1, level 0 page tables before it can identify the corresponding physical address for a virtual address. Now this could essentially take up time as well, right? And therefore, because we are losing locality, the TL the TLB, there would be a lot of TLB misses affecting the context switch overheads as well. So how do you essentially set the right amount of time for a context switch quantum, right? So in other words, the time slice for a process runs for some amount of time, which we call as a time slice. And how do we essentially set this particular time? Should it be a few nanoseconds? Should it be a few milliseconds or seconds? So that is something which depends a lot on the system and the type of application. Now, if the time slice is too short, it has certain benefits. For example, processes which are present in the runnable queue do not have to wait too long before they are scheduled in and go into the running state. But it is bad because the negative aspect of a short quantum or short time slice is the fact that there would be tremendous amount of overheads due to the context switching time, right? As we discussed in the previous slide, context switching has its own overheads, and if you do the context switching too often, these overheads essentially accumulate, making giving a lot of performance overheads or something. Yeah. On the other hand, if we keep the context switch quanta or the time slice too long, this is negative because processes no longer appear to be to execute concurrently, right? So if you keep very long time slices, the CPU or the system does not behave like a true multitasking environment. It does not feel like the processes are executing concurrently, right, or in parallel. So this too, if the quanta is too long, it may essentially degrade the system performance as well. So typically, processors or operating systems may essentially keep the context switch time between 10 to 100 milliseconds. XV6 programs keep timers at 10 milliseconds. So what we see later on is that these time periods are essentially configurable and vary dynamically based on the load of your system and the type of applications and processes that are executing on the system. Whether the process essentially requires more CPU time or less CPU time, whether it is performing something critical which can affect the user experience on the CPU. So all of this is taken into consideration to decide what is the ideal context switch time or the ideal time slice for every process.